As some of you may have said, I'm taking full credit for Gary's success to launch him as a astrophysicist. Because when we were living in Morningside, oh, let me put the recorder on. I'll start over. Hey, oh, I am recording. Okay, so we start the recording. I lived first on Jancy Street and then on Chisholm Street, half a block away. I lived between the two Melnicks, Larry Melnick and Gary. We'd walk to Morningside School every day and come home at lunch and spend a lot of time together. But when we got to about maybe middle school, we developed an interest, and certainly I did, into UFOs. Okay. And uh, I don't remember the exact sequence, but maybe Gary does. That there was a fellow that lived two doors down from me, and an older man, DJ Johns, who was single and kind of a reclusive fellow. And uh, I saw that there was a book written by a guy named Frank Edwards about UFOs. And he would write things like Stranger Than Fiction. And he was going to speak at the Carnegie uh, Library. And somehow we got tickets, Gary Melnick and myself, and DJ John took us, and we were, I don't know, Gary, maybe about seventh grade, sixth grade, I'm not quite sure, in
Yeah.
his 56 Studebaker. And we went to see the lecture on UFOs. And then at some point around that time, Earl Kaiserman lived behind Gary. Okay. And sometime we were playing out one night in the alley. And we saw a light on the roof of Earl Kaiserman's house. So we decided that we would, that was a UFO. And we had just been primed by the lecture. And so from that point on, we started to look for UFOs, okay, from Gary's grandmother's upstairs porch with our tinfoil and antennas and tape recorders. And I have to say that at that point, we didn't have UFOs, but I'm going to turn it over to Gary to tell us about his continued search. So go ahead, Gary. Thank you so much for doing this.
Okay, sure, Bob. Since I think we've evolved into sort of a multi-class conclave here, I'll just remind folks that I'm a graduate of the class of 70. Following Peabody, just to pick up on Bob's history, I attended Cornell University, where I obtained an undergraduate degree in physics, and building on the solid foundation of research that Bob and I did as kids, and he just described, I went on to get a PhD in astrophysics in 1980, also from Cornell. Following Cornell, I moved to the Center for Astrophysics at Harvard University, where I've been since. And over the arc of my now, I guess, 41-year professional career, post-PhD, I've been lucky enough to have the freedom to be able to pursue a pretty wide range of fanciful interests, a number of which touch on this question of life in the universe. And it's these projects, several of which are still ongoing, that I'll describe today. I'll just, why can't I advance this? That's interesting. Bob, let's see.
Slideshow view, because that happened to me once.
Let me,
you got to go on slideshow view and then use your arrows.
Yeah, let me see here. Darn it. Okay, I don't know if this, yeah, that'll do it. Oh, there it goes. Okay. This question of are we alone? Is there life beyond the Earth is an ancient question. Ptolemy considered it in the year 120, 130 AD. I always liked this little image of him and his muse, Astromia, considering the possibility that the heavens contain life. And of course, this question persists to today. This was a cover of Time in March 2015, dedicated to the question of, is there life in the universe? So what I'd like to do tonight is cover 5 topics from my career, starting with how do stars and planets form. This was an unsolved problem in the 1970s when I started graduate school. And the research I did in this area took me into the stratosphere more than 200 times, as I'll describe. The second topic happened after I got to Harvard, which is the search for the ingredients of life between the stars and my designing space telescopes. The third topic is the search for habitable planets. Is life unique or is it inevitable? And I'll highlight 2 projects I'm involved in, one very small and one very big, both consequential, I think. Number 4 is, in distinction to habitable planets, what can we say about inhabited planets, and in particular intelligent life? And I'll relate a couple, I think, anecdotes from Neil deGrasse Tyson and Carl Sagan that came from direct conversations I had with both of them, that I still refer to when thinking about possible communications from an advanced civilization. And I'll also discuss a new Harvard initiative that began just a couple months ago. And I'll close with something that's a little bit off topic, but was a request from Bob, and that is some work that I've done in the past couple of years relating to black holes. And that'll be a few slide epilogue at Bob's request. So let's start at the beginning. How do stars and planets form? Before life can emerge, stars and planets must form. And it starts here. This is sort of a best artist illustration of our own galaxy, spiral galaxy. And we're about 2/3 of the way out from the center of the galaxy. But of course, this top view has to be an artist's rendering, since the Earth and the Sun are not situated this high above the plane of the galaxy. In fact, we're in the plane of the galaxy. And one way to think about our galaxy is to imagine the relative ratio of the diameter to the thickness of an LP record. And our galaxy is roughly the equivalent of maybe 2 LP records stacked one on top of the other. And as I found this image online, I chuckled a bit because I realized that my daughter, who's in her early 20s, would have no idea what this is. Instead, the perspective we have from the Earth is this. We're looking toward the center of the galaxy, which is in the center of this image, which was taken from a space telescope. And all the stars, the 100 billion stars in our galaxy, lie along a relatively thin plane horizontally through the middle of this image. These darker clouds, which I'll come to again a little bit later, appear to be out of the plane of the galaxy, but only because of the perspective. They're relatively close to the sun, and they're not really that far above and below the plane of the galaxy. But you don't have to go to space to see this, to appreciate this. And I asked if Bob Cardillo was on earlier, because his Peabody talk really inspired me photographically. I love photography, and his images were just beautiful. And I came across a few that show the plane of our galaxy from dark regions on our own planet. It is not rare to be able to see this but you really need to get out of a city. This, as I note in the lower left, was taken from a park in Utah. And as I'll explain shortly, this is us 5 billion years ago, the gas and dust that's shown here. I couldn't help but include just a few images for Rob's sake, just because I really thought they were incredibly beautiful. This one struck me. This is from the Grand Staircase Escalante in Utah, and this is from Sedona, Arizona. Just beautiful, I think. And this last one, it's curved here because of the, I believe, the lens, the wide angle lens that was used. But this is from New South Wales in Australia. So let's start at the beginning. How do stars and planets form, and what drove me into the stratosphere to find out? The plane of our galaxy consists largely of gas and dust. But on occasion, there is a clumping of the gas and dust that gravity acts on and accelerates the clumping to pull the gas and dust together. Gravity, of course, is a one-way force as far as we know. So it continues to draw in material. And when it gets dense enough, at the center, a star will form, and around it, a disk of gas and dust. In time, the star matures into a star like our sun. And also in time, gravity acts to take this amorphous gas and dust and fashion it through gravity into planets. The remarkable thing is that the factor by which one goes from an initial cloud down to a star is a collapse ratio of 20 million. And that's a very hard number to get one's head around. But one way to think of it is if the initial cloud was the size of Pennsylvania, the star at the end of the process would be the size of a US nickel. Now, when you compress gas by this amount, you heat it. This is how a piston in a car works, but in this case, it's gravity that causes the compression. And if you put a thermometer inside these glass containers, the work you do in pushing down and compressing the gas goes into heating it. But a heated gas wants to expand. And the problem astronomers confronted in the 1970s was that you could show rather simply that the process of star and planet formation would self-arrest well before anything resembling our own sun and our own planets. The only way that nature could proceed through this immense collapse phase is if the gas cools, as it radiates away that heat and allows the gas to continue to collapse. So this was a question that interested me in graduate school. That is, how do interstellar clouds shed the heat that is an inevitable byproduct of the collapse to form stars and planets? To explain what I did and what drove me into the stratosphere, at the time it was thought that this heat was radiated away in the infrared. Well, you know, for some of us, it's been quite a few years since we looked at an electromagnetic spectrum. And just to remind you, the infrared is situated between the visible, familiar to us, and the microwave and radio wavelength regime. These are the wavelengths that our cell phones work at, and of course, TV and radio. And in particular, the theory at the time was that these clouds cool through radiation in what we call the far infrared. But there's a problem, and that is that water vapor in the atmosphere is a very efficient absorber of infrared radiation. And to illustrate that, if we looked at a galaxy, this is a galaxy called M51, in the visible, we would see this beautiful image on the left. But if we looked in the far infrared from an observatory, a giant observatory at one of the highest sites that these observatories are placed, which is around 16,000 feet altitude in a high dry site, 98% of the emission from the object on the left is absorbed by water vapor, and only about 2% get through. However, if we can get above most of the water vapor, and that means getting to maybe 45,000 feet, maybe a little bit higher, much less of the infrared radiation is blocked, maybe about 30%, and 70% is visible to us. So, you know, this is fairly obvious. You want to get as high as you can get and above the water vapor. And that means going into the stratosphere. The stratosphere is the layer above what envelops us, you know, as we sit here tonight, and even, you know, what we fly in when we get on an airplane. The stratosphere stretches from about 37,000 feet up to 164,000 feet. And for the purposes of carrying out this study, most importantly, it's above more than 99% of the atmospheric water vapor. So now the challenge turned to how to get into the stratosphere. The solution was to apply to use a one-of-a-kind airplane that NASA developed. This is a modified Learjet, and you'll notice, importantly, it has it's a 30 centimeter or 12-inch telescope in its side, which we did, and we were granted time on it. But before I could use it, I had to overcome a rather serious obstacle, and that is because of this hole in the side of the plane, it's not pressurized inside. It's warmed. It's a shirt sleeve or slightly cooler environment, but it's not a frigid environment. But there's very little air in there. So in order to fly on this plane, I was required to go through special training in high altitude physiology and unpressured environments. Basically, the physiology surrounding what's known as hypoxia or oxygen deprivation. I did this, I had to do it every 18 months. And what I'm showing here was one of the 3 places I did it. The other 2 was Pease Air Force Base in New Hampshire and Travis Air Force Base between San Francisco and Sacramento. This one was Lemoore Naval Air Station, about 20 miles south of Fresno, California. And I joined 12 F-14 pilots in going through this day-long education and testing regime to qualify. And this is not, I'm not in any, in this picture, but this was what the chamber looked like to simulate high altitude. I was given, along with these 12 other F-14 pilots, a clipboard and a piece of paper. And of course, preceding this was a whole description of the physiological effects of oxygen deprivation. You'll notice at the ceiling level, there are 2 gloves, and they were tied at the wrist. And as they began to pump down the chamber, you saw these gloves expand, and almost to the point where I was certain one or both would probably burst. They didn't, though. But what they asked us to do to sort of illustrate the effect of high altitude was for each of us to write, just sign our names over and over and over again as they took the chamber to higher and higher equivalent altitudes by pumping out the air. And it was really interesting on 2 accounts. One is, as I was doing it, I was 100% certain that my last signature was every bit as good as my first signature. The other thing was you begin to lose your color vision because the absence of oxygen affects the cones, the rods and the cones, but I think it's mostly the cones in your eyes that give us the majority of our color vision, and the room turned to black and white. once they lowered the altitude again, of course, as you might predict, the signatures just turned into a scrawl, an unrecognizable scrawl. So it was quite interesting to see how the mind can deceive you into thinking you're perfectly fine when in fact you're absolutely not. And the loss of color vision actually saved me on one flight, because as I was working at altitude, I looked down at the sleeve on my left arm and I noticed that it was black and white and it was a red plaid shirt. So I immediately tightened the straps on my oxygen mask, took a few deep breaths, and with each breath, the color returned. It was really, almost psychedelic. But this training is obviously intended to alert one to these sorts of hazards. So here I am on the right. That's me in the plane on our way up to the stratosphere. With my oxygen mask and the helmet that I'm sure would have protected me if I had fallen out of the plane. On the left is the equipment. I'm sitting on the right on the stairs on the left, which when the door gets closed can actually be sort of a crude seat. And that's where I am on the right. I did this 227 times in the course of gathering the data for my PhD thesis. One little side anecdote that still cracks me up when I think about it is that I think I was near the end of this string of 227 flights, fortunately, when I was out on the flight line checking the oxygen and the kinds of things that you do before the flight. And a NASA person whom I knew was guiding a woman I learned was a teacher, and about a half a dozen kids with her. And the NASA guy said, "Can they ask you a few questions?" I said, "Sure." And we spoke for a few minutes, and then one of the kids said to me, "What do you do if your nose itches?" And I never thought about it. In 200 flights, it never occurred to me. And that night, that's all I could think about. But you can't take your mask off because you only have 3 to 6 seconds of useful consciousness at the altitude in the plane. So I just had to sort of try, it was mind over matter to get it out of my mind. And fortunately, on my few subsequent flights, I was busy enough that it didn't bother me again. At any rate, so this was the culmination of my graduate school work. And I'm proud to say that we solved most, but not all of the open questions related to how clouds shed their energy as they collapse to form stars and planets. Nature being subtle always leaves a few questions to be resolved later, but I'm happy to say that I think my PhD thesis was well received. After finishing my work at Cornell, I went on to Harvard, and my interest turned to the ingredients of life between the stars. No planets around other stars had yet been detected, but people were just certain that they had to be there, just on simple physics grounds, and the fact that why should our solar system be special? And so I became interested in designing space telescopes, and in particular, with a team I put together, designed a telescope to look for water in gaseous form between the stars, and molecular oxygen and a few other species, and to measure their abundance. So NASA 3 or 4 times a decade will release what they call an announcement of opportunity for anybody to propose a mission in the sort of at that time, $200 million class. And the team I put together was one of, I think, 52 proposals NASA got in that round. And we were very, very lucky. We got selected, and this was the satellite, sorry, that we designed, an artist rendering, obviously, of it in orbit. And it was launched on December 5th, 1998. I mentioned this in my reunion Zoom call, my short one, but I don't know if there are new people on board. I'll go through this real quickly. If you look up in the night sky in the winter, you'll see 3 stars in a row that are rather conspicuous. You know, it's starting in November and December. And below the middle star are 3 fainter, what appear to be 3 fainter stars. But in fact, the middle star is not a star at all. It's a nebula. And it turned out that this nebula, and this is a Hubble photo on the right of this, not a star, but a nebula. And it turned out to be the region among the 8,000 or so that we studied with this satellite that was producing the most water. And to put it in perspective, converting the strength of the water line, the gas phase water line that we measured, into a production rate of water molecules, it was enough to fill the Great Lakes 30 times every second and fill the Earth's ocean every 24 minutes. Now, this is over a big area, bigger than the Earth, but I always found that conversion to be interesting. So we saw water everywhere, but aside from this region, it wasn't as abundant as we had expected from predictions. And for a variety of reasons, detailed reasons, we inferred that we were just seeing, you know, literally and figuratively, the tip of the iceberg, that 99% of the water between the stars is frozen deep within clouds. Now, what do I mean by frozen? This is a picture of the Eagle Nebula. It's within our galaxy. It's one of thousands of nebulae within our galaxy. And these dark areas here are dark due to light that's blocked by trillions and trillions of very small dust grains. It's what produced the dark lanes in my earlier images of the galaxy. Now, what are these grains? These grains are small. They're about 4 millionths of an inch in size, and if it helps at all, that's about 1/100th of the diameter of a human hair. But what works better for me, and maybe for you, is that it's about the same size as the little particles that come off in cigarette smoke. But these dust grains are very cold. And when molecules of water or carbon monoxide or carbon dioxide or methanol that are shown here hit the grain, which they do frequently, it's so cold that they freeze onto the grain. And over time, these grains can build up a pretty thick ice mantle. And so when we talk about water being frozen, it's frozen on the surface of these tiny dust grains. But if these dust grains participate in the collapse that I showed earlier to form stars and planets, then interstellar water is most likely the source of the Earth's oceans. In this evolutionary sequence I show here, these icy grains follow the gas in forming the disk and then eventually the planets. And in fact, I happen to think that these icy mantles actually accelerate the assembly of planets, much as ice cubes in our ice trays stick together when these ice-covered grains collide with each other, which they will as things get denser. The ice on ice actually makes them stickier. And you go from these very tiny grains to millimeter-sized grains, centimeter, to tiny pebbles, to kilometer-sized rocks, and you're well on your way to building planets. So it turns out that I think one of the results of this satellite mission was our supposition that water on Earth, every water molecule on Earth, was formed actually in the clouds between the stars. Now, the other thing the satellite was intended to do was to look for molecular oxygen, but we didn't see it anywhere. In 8,000 lines of sight across our Milky Way, we didn't see molecular oxygen anywhere, which was a big shock to us. And I have to say, as the leader of this effort, I became concerned 2 years into the mission of not detecting it at all, whether it was truly absent in space or whether the observatory was faulty, whether the detector that was designed to detect molecular oxygen wasn't working. So 2 years into a 6-year mission, I just said, I can't go through 4 more years and end this mission without knowing which of these two possibilities is true. So the only source of molecular oxygen, I was certain that, well, the source I was certain contained molecular oxygen was the Earth. But NASA forbade us from looking either at the sun, which would have destroyed our detectors, or the Earth, for fear that it would overload the detectors and do damage. But as the person who built this satellite, I knew what it could do, and I was pretty confident that we could look at the Earth for a short time. But there are all sorts of software safeguards built in to prevent us from slewing the spacecraft and looking at the Earth. So over a weekend in, I think it was the year 2000, my team and I got together and we figured out a way to override the multi-layers of safeguard on the satellite. And over a weekend, when the NASA staff was sort of skeletal and we thought we could get away with it, we slewed the spacecraft toward the Earth for only about 5 seconds. But clearly, you know, we detected molecular oxygen. And this is just a few seconds of data. And so I was greatly relieved that we hadn't launched a broken satellite. But this turned out to be very consequential because the non-detection of molecular oxygen in space means that the Earth didn't inherit the molecular oxygen we're breathing right now from its formation. That instead, along with other lines of evidence, I should say, molecular oxygen arose on Earth as a consequence of the emergence of plant life and photosynthesis about 3.5 billion years ago. So having not detected the gas phase water, and that satellite that I just showed you was incapable of detecting the emission and absorption from solid state water, ice. In 2012, I, and along with a group of other people, designed a follow-on satellite to look for the missing water in water ice and other building blocks of prebiotic molecules. And so we again designed the observatory shown here called SphereX. We put in our proposal along with many others, crossed our fingers, and lightning struck twice. NASA selected us. This was is about a $300 million mission. I spoke about this mission at the reunion Zoom, but on another topic, what powered the Big Bang. Today, I'll focus on how the key ingredients of life are delivered to newly forming planets. So as I allude to, this mission has 3 major science themes within it. I spoke to studying the first billionth of a billionth of a billionth of a billionth of a second of the universe last time. I am actually the science lead for this survey of prebiotic ices in the Milky Way. And this third theme is another hour-long talk. Now, where did we get the name SphereX? I liked it because I've always liked this image, which I think originally was a wood carving, but has been most frequently shown as an image like this. This is from Camille Flammarion's 1888 book, L'atmosphère météorologie populaire. That's my Peabody French training speaking. And it shows somebody looking through the spherical canopy of stars and looking beyond them to find the gears and the mechanisms by which the universe works. The other reason for selecting Sphere X is somewhat more mundane, but it is accurate, and it's how this satellite will tile the full sky in every direction as we orbit the Earth, and then the Earth orbits the sun. But NASA being NASA, they like these names to be acronyms and to mean something. So after selecting the name, we reverse engineered a NASA-EASE name for the mission, which is the Spectrophotometer for the History of the Universe, Epoch of Reionization, and ICES Explorer. And to be honest, I had to look it up for this slide. We use it so infrequently that I never remember what it stands for, but NASA likes it, and they're paying the bills. So Sphere X will obtain more than 1 million measurements across the disk of the Milky Way and measure the abundance and distribution of water ice, carbon monoxide, carbon dioxide, this is methanol, all in ices, and other prebiotic ices across the Milky Way. The launch of this satellite is in the summer of 2024 from Vandenberg Air Force Base in California. And as I say, we hope to determine the origin of the Earth's life-enabling water and prebiotic molecules with a 5,000-fold improvement over any previous measurement. So let me move on to the search for habitable planets and this enduring question of whether life is unique or inevitable. And I'll illustrate what I've been involved in terms of a very small project and a very big project. On the small end, and I don't mean that it's small because there are very few people involved. In fact, it's a growing number of people. It's something that started at Harvard University called the Origins of Life Initiative, and it brings together about 150 researchers in the 8 departments that I list here, dedicated to answering the question, is life abundant in the universe? A sample of the projects that are underway are, how to identify Earth-like planets around other stars, being done within our astronomy department. How did the Earth inherit its ingredients of life? That's fundamentally what I just described, also within the astronomy department. How the Earth's history affected the evolution of life, both geological history, meteorological history, etc. And this last one, which you may find quite interesting, I certainly do, is the making of life from scratch, molecular biology. And what do I mean? At some point in the Earth's history, there was a transition from chemistry to biology, to living organisms. Is that a transition that's easy or hard? And in particular, what kind of environment and what ingredients would you need to make inanimate matter into a living cell? Now, you might think that these are the doings of a Dr. Frankenstein or some crazed egotist. But in fact, this effort is being led by Jack Szostak in the Department of Molecular Biology, and he was the winner of the 2009 Nobel Prize in Physiology or Medicine. Now, I don't think I could say it better than him, but this is sort of the goal of his work. If we can actually show that there's a continuous pathway to life with no super hard steps along the way, then we can conclude that it's likely that there's abundant life out there, meaning around other stars. I'll add that Jack actually is very encouraged by his work to date, and he exudes a lot of confidence that within the next 10 years, he can actually create a living cell from inanimate matter, which would of course be a scientific milestone. The big is truly big. Every 10 years, the National Academy of Sciences is mandated by Congress to recommend astronomy priorities to NASA. And this is how multi-billion-dollar missions get approved. Things like Hubble Space Telescope and the James Webb Space Telescope, which is the next huge observatory to be launched, hopefully this December, all came about as a result of being the #1 priority in this National Academy study. So in preparation for the 2021 decadal survey, I served on one of 4 mission study groups to offer the National Academy 4 options for very expensive missions. So I was involved at sort of the 50% level of my time in the study of something called the Origin Space Telescope. It's about 2.5 times larger than Hubble and 1,000 times more sensitive than anything before. And we submitted our report to the Academy in August of 2019. I'll call your attention to the sweeping scientific thrust of this mission, which is to study the first stars that were formed in the universe some 13 billion years ago, all the way up to is there life on other planets? So let me focus on this second tagline here. And let me just say, I wish that I could have shown the Hubble Space Telescope next to the Origin Space Telescope rendering here to appreciate the enormity of this telescope. Focusing on the one slice that this telescope will do is the follow-up study of known planets around other stars, otherwise known as exoplanets, exo meaning outside of our own planetary system, of which there are about 4,500 known and confirmed planets around other stars. About 175 of these 4,500 exist at just the right distance from their parent star, that they inhabit what astronomers often loosely call the Goldilocks Zone, meaning that these planets are not too hot and they're not too cold, such that liquid water can exist on the planet's surface. And to our understanding, liquid water is essential for the emergence of life. Now, this plot, I promise you, is the only plot in my talk, but it highlights something I think is very interesting. Every one of these circles is one of these 4,500 detected exoplanets, and there are many more outside of the bounds of this plot. But along the horizontal axis is the planet's surface temperature, and the vertical axis is the size of this planet in units of the Earth size. So 1 on the vertical axis is the Earth size. And what I find quite interesting about this plot is that there are, more than a few planets that are 6, 8, 10, 12 times the size of Earth that could have oceans and rivers and lakes. But because of the mass of these super Earth-sized planets, the physiology of any advanced creatures that develop on these planets will be quite a bit different than that developed on the Earth. Were we on a planet 10 times the size of Earth, we would barely, if at all, be able to get out of a chair because of the gravity, and we certainly wouldn't be able to walk. So any creatures that develop on these exoplanets are bound to have a different appearance than Earthlings, despite our movies, and in all likelihood would be bigger, certainly more muscular, bigger boned, and so just this information alone should dispel any notions that all of these planets will have creatures that look like us, but wear silver uniforms. So the Origin Space Telescope will look for habitability by looking for features in the atmospheres of these 157 water-bearing exoplanets. And what can we tell? So don't worry about the horizontal and vertical axes. The key thing here is to determine whether these planets are habitable and possibly contain life, though not necessarily intelligent life. The detection of water and carbon dioxide would tell us that the necessary ingredients for life are present on this planet, but it doesn't say that there's life. We need water, we believe, to form life, and CO2 for plant growth, if photosynthesis is dominant. However, we'll also look at species like ozone, which is a product of molecular oxygen, and methane, which on Earth are only produced through life, I mean, in the majority. So the presence of molecular oxygen or ozone and methane in the spectra of these exoplanets would be a pretty strong signal that there is life. Intelligent or not, there is life. So let's move on to the question of, is intelligent life common in the universe? And I'd like to relate two stories of conversations I've had with two astronomers you may know, Neil deGrasse Tyson and Carl Sagan, and then I'll move to a new Harvard initiative. So apropos this topic, I'll mention that we're 1 year into a project called Breakthrough Listen. It's $100 million over 10 years that was donated by a Russian-Israeli entrepreneur to carry out this study. And the money is going to buy telescope time on these three large radio telescope complexes. The one in West Virginia is in Green Bank, West Virginia. And to give you a sense of scale, you could put Heinz Field inside the size of this dish. It is huge. And there's one in Australia and one in South Africa. And the selection of sites is intentional so that if a source from which signals have been detected are setting for one telescope, they're rising for the next one. And there should be an ability to have continuous listening if something of interest is detected. So the intent is over 10 years to listen to 1 million of the closest stars, and it's sensitive enough to detect common aircraft radar, such as, is in, the greater Pittsburgh Airport, Logan Airport, Dulles, to detect the airliners coming in for a landing. These are sensitive enough to detect those radars from any of the 1,000 nearest stars. So this would give us, some encouragement that, maybe we'll find out by eavesdropping on other civilizations. But there's reason to be humble. Neil deGrasse Tyson came to our department several years ago to give a colloquium. And I was chatting with him, with a few graduate students around. And one of the graduate students asked him, his assessment of the success of this listening effort. And Neil made a good point that always stuck with me. And that is, I think it's hubris to think that we would have any chance of understanding a transmission from other beings. And the reason is chimpanzees and humans are about 98% the same. And add to that, we evolved on the same planet. We evolved breathing the same air with the same environment. And yet, if you sat across from a chimpanzee and said, I am going to take a taxi to Greater Pittsburgh Airport and catch a flight to San Francisco, there isn't a single word in that sentence that this chimpanzee would understand. And so I don't know what makes us believe that if we were eavesdropping on another civilization, that we would have any chance of understanding what they're saying. The second humility reminder comes from Carl Sagan. You may remember him. I mean, he was a popularizer of astronomy in the 70s and 80s and 90s. And of course, he was the one who wrote the book that evolved into the movie Contact. Carl was a professor at Cornell University, and I took a course from him, and we, meaning, you know, some of the graduate students, would meet with him over lunch, you know, once a month or so. And Carl was fond of telling the following story. He had a conversation with the famed cultural anthropologist Margaret Mead in the very early 70s. And as Carl told it, Margaret said that she had discovered just a few years earlier people living on a small cluster of islands in the South Pacific that hitherto had no contact with any other people on Earth. And they communicated amongst their little islands by going up to the highest point on their islands, making a fire, and modulating the smoke from that fire with palm fronds. And she said that they would communicate things like where there's good fishing today, you know, when they're going to come over to the other island. Everybody was sort of related, just sort of the mundane facts of life. But they, like us, apparently were very curious as to whether they were the only people in the world. And so periodically, they would pick the one or two people amongst them that had the most acute vision, you know, usually somebody in their late teens or early 20s, and they would ask this person, you know, periodically to go up to the highest point amongst these islands and just scan the horizon looking for other smoke signals. Now, they were doing this up until the late 60s. And as they were doing this, these people were totally unaware that not only were there 5 billion to 6 billion people at that time around them, but that millions of radio signals and television signals were going through their bodies at that time. So, you know, it made Carl wonder, much as he was an advocate of reaching out to other civilizations in the galaxy, whether we have any right to expect that using our 20th and 21st century technology, we have any expectation, reason for expectation, that these civilizations would be communicating via radio waves, much like this group of people communicated with smoke signals. And the thing to keep in mind is that our universe is almost 14 billion years old. Our solar system is about 5 billion years old. So to imagine that there are other technological civilizations that may be hundreds, thousands, or millions of years ahead of us is not at all unreasonable. What may be unreasonable is the expectation that a civilization 1,000 years ahead of us would still be communicating via radio waves. So we'll see. If you don't look, you won't find. But there are a number of reasons to perhaps expect that this breakthrough listen effort, you know, may not yield anything. But as I say, it's worth a try. You know, it's high risk but high benefit. Let's put it that way. So. This last thing under the category of how common is intelligent life is a relatively new Harvard initiative. It was started in June of this year, and its impetus was this detection of an object by telescopes in Hawaii, of a very oddly shaped object on a trajectory that was clearly not suggestive of its origins in our solar system. I show the trajectory in the lower right. The key thing to take away is it was coming at us from well above the plane of our solar system and on a trajectory that was not orbital. It was a one pass through our solar system. It was given the name by the Hawaiians who detected it, and the first detectors of an object have naming rights, and they gave it a Hawaiian name, Oumuamua, which in Hawaiian means a messenger from afar arriving first. Now, what made this very controversial is that after passing through the sun and moving away from the sun, it's very straightforward to calculate how it should slow down under the gravitational influence of the sun. And this object, Oumuamua, was slowing down, but not at the rate given by Sir Isaac Newton's equation for gravity. So this stirred a lot of interest, and a member of our department, Avi Loeb, became the face of the small but maybe growing community of astronomers who said that this might be alien technology, that it's evidence for some propulsion, perhaps, clearly indicates something that is not rock-like, but that has some technology behind it. And he was all over the news this past year. You may have seen him. So why am I mentioning this? I wasn't involved in this in any way, but about 3.5 weeks ago, Avi reached out to me and asked for my help in this project. Because I like Avi, and at some level, it takes me back to Morningside 50 some years ago or more. I said, yes, I'll help him. So, the idea is that rather than listening for radio signals, what he terms the Galileo project will search for and study actual physical objects of believed extraterrestrial origin. And this includes these sightings that were highlighted in the New York Times of objects that were seen and tracked by Navy aircraft. So the idea is that the Galileo project at Harvard will conduct a multi-wavelength search in a very transparent manner using scientific methodology, and all the data collected will be made available to researchers around the world. There'll be no reliance on anecdotal observations or partially declassified data. We don't know, for example, whether the military is releasing everything they know about that object in the lower right, but anything that this Galileo project detects will be released in its entirety. So that's something that I'm into now for about 3.5 weeks. Let me close with a request, and this is now shifting gears away from life in the universe to black holes. And this was something that Bob asked me to present. So most people probably have seen this, at least in the astronomy community, this iconic picture of a black hole. It made headlines around the world. I mean, literally, there was probably no corner of the world that didn't carry this picture. And this black hole sits at the center of a galaxy known as M87. The black hole's mass is known from measures of this image and other measurements to be almost 7 billion times the mass of our sun. Fortunately for us, it's about 55 million light years away from us and poses absolutely no danger to us. This image was released on April 10th of 2019, and it was led by a fellow who resides at the Center for Astrophysics, only 2 doors down from me. Shep Dolman was the person who pulled this all together in something that he dubbed the Event Horizon Telescope. Now, what is it? It's basically a very laborious and technically challenging linking of telescopes from around the world such that they act like one single telescope the size of the planet Earth. So effectively, you have a telescope that's about 7,000 to 8,000 miles in diameter. When I saw the image, I had the same reaction that I think Rob Cardillo mentioned when this came up during my Zoom talk. Why isn't this image sharper? And I had the same reaction. And then it occurred to me in April when this was released, that if I modified the design of this Origin Space Telescope I described earlier, shown here in the lower right, it could act as one of the telescopes in this array of telescopes around the Earth and create, instead of an 8,000 diameter mile telescope, a telescope that was effectively 1,000,000 miles in diameter, which would improve the spatial resolution of that image by a factor of 120. So working with members of Shep Dolman's team, mostly this person, Dominic Pesce and Carrie Harworth, two postdocs working with Shep, I wrote up this proposal to the National Academy, informing them that if the decadal survey selects the Origin Space Telescope, we can improve the resolution of these black hole images by a factor of more than 100. And we should know what the National Academy decides with regard to the Origin Space Telescope within the next 6 months, hopefully. And with that, I'll thank you for your attention and stay tuned for further results.
Okay, wonderful, Gary. Why don't you stop the screen share and let the
Yep.
classmates ask you some questions?
Okay.
And I'll take the liberty. What is the actual project? I think I remember you telling me you're working on a big project now.
Well, it's the Sphere-X, which
So that's the big project.
is
Okay.
big because it looms relatively soon. You know, it's coming up fast. Yeah, so I would say that most of my time is working on that. Of course, if Origins is selected, I may pivot to working on that, though that has a launch date in 2035. So I'll be about 84 years old if I'm still above ground. So, you know, what I may do if it's selected, and who knows, I would probably want to spend a lot of time on that and at least get it started.
Okay, let's open it up for questions. I think the easiest, because I can't see everybody and record properly, is if anybody has a question, unmute themselves and talk and just be patient. We'll do it one at a time. So who has a question here? Or a comment? Go ahead. Anybody?
This is Rick.
Go ahead,
Gary,
Mr. Steinberg.
fascinating presentation, just unbelievable. First of all, any more planned trips to the stratosphere for you, or is that line?
No, I mean, as I mentioned on the Zoom call, a frustration that I will carry to my grave was that working with a group of people at the Center for Astrophysics and the University of Arizona, we built a telescope that flew on the space shuttle in 1985. It actually flew on the Challenger in 1985. And when the Challenger, and so I submitted my name to fly on a follow-up flight. Because the shuttle lands and you can recover your payload, I thought of a way to modify the telescope to do different science. And because of my love of flying, I submitted my name to be what they call a mission scientist, which would fly aboard the shuttle. And I know that would have been a dream come true for me. But actually, the Challenger, of course, met its fateful demise in January of '86. And that program under which the telescope we built flew ended. And that's when I started thinking about this satellite to detect water in O2. I love flying. To me, as much as I've enjoyed on many levels these satellite projects, I think the most pure joy I've experienced was flying up into the stratosphere in that NASA jet. It just was so much fun for me.
Wow. So it beats the Thunderbolt at Kennywood.
It's close, but it does beat it.
Actually, my real quick other question, the Goldilocks Zone, give us a rough range, what temperatures we're talking about?
Well, we're talking about where water is in liquid form. So it's the distance of a planet from its star such that it's heated by that star to a temperature, the surface temperature between 32 Fahrenheit and 212 Fahrenheit.
Gotcha.
So and you know, that distance varies depending on the brightness of the host star of that planet. But there are, you know, over 150 planets that are just at the right distance where if there's water there, and we'll find out with this Origin Space Telescope, then it's very likely in liquid form on the surface.
Wonderful. Thank you. Appreciate it. Great presentation.
Okay, anyone else?
Hi, Gary, can you hear me?
Yeah.
It's Rob. Hello. Hey, I don't know if you can see me or not, maybe not. Hey, great presentation. I really enjoyed that. It just blew my mind so many ways. The Origin telescope, would that be an Earth orbit telescope? Or would that be like the James Webb telescope that's going to go to some nodal point way off that's not going to be reachable for any possible repairs in the future? What's the Origin like?
You're exactly right, and I apologize for not mentioning that. Yeah, it's in spaceflight parlance, it's going to a Lagrange point. It's a point between the Earth, Moon, and Sun where the gravity just balances. And if you place an object there, an observatory in this case, at this point, it takes very little propulsion to keep it there, because it's just balanced between the forces of gravity of these three objects. And that's about 1 million miles from Earth.
Yep, great. Thank you so much. Great talk.
Okay, anybody else?
I have a quick question.
ahead.
Gary, you know, you talked about like this possibility that there could have been civilizations out there, you know, but they could be 1,000 or 1,000,000 years ahead or behind us or whatever. Like, what about just the time between the civilizations? You know, say something existed that was exactly where we are right now, elsewhere in the universe. I mean, like we might not hear about it for 100,000 to 1,000,000 years.
No, well, you know, that's exactly right. Is that it's very difficult to carry on a conversation because it could take the closest star with a known planet around it, Alpha Centauri, is 4.3 light years away. So if they broadcast to us and say, hello, how are you doing? It would take 4.3 years to reach here, and then 4.3 years for us to reply, and another 4.3 years for them to come back and say, got your message, thanks. And that's the closest star. So yeah, I mean, it's these are all challenges that puzzle those of us who think about, you know, how might a multi-star civilization work. And you know, it's either that they're advanced enough that, you know, they've increased their lifespan to hundreds of years, such that the distance, you know, if it takes 20 years to go between one star and another, that's still a small fraction of their lifespan. The other is that they may not have the expectation of communicating instantly with each other, but just seed their civilization amongst many places as a hedge against being destroyed. I mean, our civilization could be destroyed tomorrow with an asteroid hit. I mean, it's what destroyed the dinosaurs. So if you're a looking civilization, you actually want to distribute your species on many planets and possibly many stars. It will be the case at some point that our sun devours the Earth. I mean, fortunately for us, it won't be for about 5 billion years. But we know stellar evolution well enough to know that in 5 billion years, the sun will begin to run out of its fuel. And for a variety of reasons, it will swell to basically encompass Jupiter's orbit. And the Earth will just be burnt into a cinder. Now, that's 5 billion years from now, but other stars behave the same way. So there are incentives for civilizations to spread out. There are crazier ideas that may be true, and that is that, I mean, two things. One is regarding communicating with civilizations. You know, civilizations might reach a point of advancement where they have created essentially a utopia for themselves, and they have no interest in advertising their presence around the galaxy. That is to say, they intentionally are radio quiet because they don't want to attract attention. Another possibility is that organic beings such as ourselves may be transitory in the scheme of the evolution of civilizations. And what I mean by that is that computer technology and AI is only 100 years old, or less, actually quite a bit less. If you extrapolate and we don't destroy ourselves, you know, what might intelligence mean 1,000 years from now? It may be that the most intelligent creatures on Earth are silicon-based, you know, with much more intellectual capability, memory, and speed. And when that happens, you essentially have a civilization that is run by entities that have an indefinite lifetime. And so either sending out probes or actually transporting themselves to other stars that could be 20, 30, 40, 100 years of high velocity travel away is not at all unreasonable. I mean, these are all guesses, of course, but you know, they're relatively minor extrapolations from what we know now.
Thank
Hey,
you. Great
anyone,
answer. Thank you.
anyone else?
Hey, Gary, Lee, Paul.
Hi, Lee.
How you doing?
I'm doing great.
Quick question. Any thought to hitching a ride with Bezos or Branson?
Sure. I mean, if given the opportunity, I don't know whether I want to pony up 4 years of my daughter's tuition to do it. And in some sense, I think I'd be frustrated with, you know, 5 minutes of weightlessness.
Okay, so that actually leads me to a serious question. What are your thoughts on corporate space adventures?
I think they're great for the following reason, is that they're driving the technology. And, you know, while, you know, I may not be totally sympathetic to the notion that only billionaires can, or multi-millionaires can enjoy the experience now, these companies like Bezos and Branson, Richard Branson and Elon Musk, they've developed launch vehicles that add to the capability of what NASA can do. And, you know, they're becoming reliable enough that NASA no longer has to spend our taxpayer dollars on developing rockets. They can just buy a ride on one of these commercial vehicles, and NASA can use its resources to do more challenging things. So, you know, again, you know, I think on the technology front, it's a great thing. On the business side, you know, maybe it's too skewed to the wealthy right now, but,
okay.
you know.
And then
They claim the price will come down and it will be available to more common people, but we'll see.
Well, that's like commercial flight in the startup days. One more
Exactly.
quick question. How much credibility is given to the Navy pilots that saw something that was unidentified?
Well,
Because remember, they are Navy pilots and not
Yeah.
Air Force pilots.
Yeah, I mean, they're certainly more credible than, people in the backwoods who say that they saw something moving across the sky, this or that. But, it's the reason this Galileo project was started, that we don't have access to everything that the military knows. And so it's really hard to assess the meaning of the videos that they've released. They're intriguing, and they're one of the reasons this Galileo project was started. But I think it's just what kicked off the interest is sort of where we're leaving it, and not trying to read too much into these 30-second videos that the military releases.
Okay, thanks.
Okay, we have about 5 more minutes for questions. So anybody else?
I just have one question, Gary. Can Mars sustain human life?
Potentially. I mean, not in its unaltered form. The atmospheric pressure on Mars is 1/100th that of the Earth. So along with the fact that its atmosphere is mostly carbon dioxide, and we would suffocate just taking a breath, we would suffocate by virtue of the fact that the air there is very, very thin. But there are ways of, I guess the term is terraforming Mars, and that is within enclosed structures where the atmosphere contains the requisite amount of molecular oxygen. It's believed that with irrigation, that the soil on Mars could grow plants, and so one can imagine enclosed colonies in which they're self-sustaining by virtue of the plants that they're able to grow. And of course, when you have the plants, as I alluded to earlier, they are a natural source of molecular oxygen. So the humans and the plants could exist symbiotically. So I think, the big push for Mars is precisely the hope and expectation that with a little bit of work, it could be converted into something that's habitable within the limits of enclosed structures.
I mean, how long would it take to oxygenate an enclosed structure with photosynthesis?
Well, I mean, I guess I'm not sure I know the answer to that, Ron. Initially you would take up oxygen and just fill a space with oxygen. And there are ways of recycling oxygen. They do that on submarines. They do that on the space station. So it's not as though the oxygen that you take up, once it's breathed and you exhale it, you have less and less oxygen until you suffocate. The technology exists to recycle the oxygen, and certainly any plant life that you're able to grow there makes the task even less challenging.
Thanks.
Gary, quick question.
Sure.
Good to see you. Great presentation. Sorry I missed the earlier one. We're talking about Mars. Does Mars have enough gravity to keep oxygen from dissipating into outer space?
Well, of course, it would have to be in an enclosed space. So the enclosure by definition would keep the oxygen in. And the answer is yes. It has enough gravity to keep its carbon dioxide atmosphere. So the gravity isn't the problem. It's just that if you tried to do something out in the open the oxygen would just be overwhelmed by the carbon dioxide and people would suffocate. So, for the foreseeable future, any transplant of humans to Mars would have to be all with an enclosed structure, and that would make the problem that you suggest sort of irrelevant.
Okay, but keep in mind that carbon dioxide is somewhat denser than oxygen, so you wouldn't need as much gravity. Yes, no?
Well, yes, but irrespective of that, you would have to produce so much molecular oxygen that 20% of the Martian atmosphere would have to be molecular oxygen. Now, whether you would have to replenish it regularly, but just the task of getting to 20%, even if it doesn't escape, is beyond our technology right now. So you have to do it you have to build a human-friendly environment locally in enclosed structures, for the next probably couple hundred years at least.
Okay, one final question or comment, and then anybody else?
I got another question for Gary,
Yeah,
just a
Rob?
quick one. Your work takes you right up to the edge of science fiction. Any books or movies that really tickle your fancy? Anything that's really gotten under your skin? Love to hear that.
It's funny. I saw an ad on TV. My wife and I were watching the other night for the Foundation trilogy by Isaac Asimov. And I mentioned to my wife that to this point in my life, that is the only science fiction I've ever read. I've never, for whatever reason, you might think that I'm a fanatic about science fiction, but I guess science fact interests me enough that, aside from, of course, being a Star Trek fan and, enjoying Star Wars when it came out, I'm not a huge devotee of science fiction.
Hey, Gary, real quick, because I missed the beginning. What toted you up to the stratosphere? What plane?
It was a modified Learjet.
Okay.
So it had more capable engines in it that could take us up there.
So you got to what, 60,000?
Well, it's about, a little over 50 to 55,000 feet on our best days.
Okay.
Yeah.
Okay, well, thanks. Let's give a round of applause to our lifelong friend and colleague, Gary.
Thank
What
you.
an amazing talk, and I presume that one of our 3 recordings will be sufficient and will make its way to the YouTube channel, because this is wonderful and fascinating, and I can't thank Gary enough for the hard work he put to pull this all together for the classmates. And he mentions his daughter, who is a student at, of all places, the University of Pittsburgh. So his daughter Hannah is here in town. And, Gary, you know that she has lots of friends here if we ever need to entertain her or something. She's here, we're here, and we're looking forward to seeing you at the reunion.
Yeah.
So with that, we'll shift gears.
I'll just say, Bob, that there's nothing a 20-year-old looks forward to more than being descended on by a bunch of near 70-year-olds.
Yeah.
But it's comforting to her father to know that.
Yes. So with that, I'm going to stop the recording and ask Donna and the nation to allow us to do that event.